so let's chit-chat about the lab, which might have caused you a little bit of pain and suffering.
Indeed. Yes, it really did.
So
Yeah.
here's your position time graph, okay? So I can't emphasize this enough. Your position time graph and your velocity time graph have to show the same thing happening at the exact same time, okay? So you can't have your position time graph showing that you have negative velocity if your velocity time graph shows that you have positive velocity, okay? It's telling two different stories. Now, you don't know which one is the physical reality. So, Maggie, let's start with you. Maggie, what was your elapsed time interval at the end of that second interval? When it was at 3 meters, what was that time?
2.85 seconds.
2.85, not 2.58, 2.85, right? Okay. So at 2.85 seconds, okay, visualize what was happening. If I'm Maggie's group, or whatever your group is at the end of that second interval, that's when that card had hit the wall and that spring was fully compressed and you would come to a stop. Which is why when you come up here on that tangent line, if you drew a tangent line to that point, that's when your velocity would be 0, because that's when you stopped, that's when you're changing direction. Okay, so at this point, a couple of things have happened. We were rolling along, slowing down a little bit, we hit the spring. At that point, a big force began to act on the cart. I know that because the cart slowed down rapidly. So at this point, we've stopped. Okay, because remember, there's 3 things that has to happen for you to change direction. You got to slow down, stop, and speed back up. So when this thing hits, okay, that's the slowdown part. That's transferring what we call kinetic energy into potential energy. Okay, so at this point, Mother Nature has stored a bunch of potential energy in the spring. Mother Nature doesn't like potential energy because somebody said something about Snapchat, Instagram, whatever. Okay, pick your social media. Maybe they made a horrible TikTok video. I don't know. Okay. They don't like each other. So Mother Nature goes, I'll go back to kinetic energy. When she does that, she changes direction, okay? She doesn't keep going through the wall, which would be cool, right? It's like, oh, we're just going to keep going through the wall. Can't do that. So the only option is to push that back. So one of the things we'll talk about is that Mother Nature is a lazy prima donna. Mother Nature is only going to do what's easiest for Mother Nature to do. So Mother Nature at this point has a choice to make. Mother Nature goes, I can keep this thing compressed, and I can stay like this, or I can push that back and take that potential energy and change it back into kinetic energy. Mother Nature goes, that's easiest, because to keep this compressed, that's awkward. I want to go back to moving. So she does. She goes back to moving. So that's what's happening very rapidly up at the top of that peak. Now, on your velocity time graph, here's the first thing that I'm going to do. I'm going to look at the front side of your paper, and I'm going to find the sum of that second interval, okay? So in this case, if I'm looking at Maggie's paper, I'm going to find that 2.85 seconds. And at 2.85 seconds is when that velocity time graph better be crossing through 0, okay? Because that's what's happened at that point. Now, here's the problem. You don't know all these exact data points. You have to extrapolate, okay, and kind of think through what's happening. So if you think through what's happening, the cart's rolling, okay? And it has its biggest positive velocity when you're starting off. Because it's always going to be slowing down as it rolls in, and it's going to be slowing down when it rolls back. So you know at time 0 is when you're going to have your biggest positive velocity, okay? I know that's when it's going to be going fastest, because it's going to be slowing down after that. Assuming that you have good data, and some of you have data which makes it speed up, which was weird. Okay, so basically this thing is going to roll along. Now, if I'm Maggie, I'm going to go back 1/10 of a second, and that's the calculation that I have you do down below. So to figure out when it hits, okay? To figure out when it hits, you're gonna take that midpoint of 2.85. If I'm Maggie, I'm gonna subtract a tenth of a second, and that's gonna be 2.75, because what we're assuming is that from the time that it comes in contact with the wall to the time that it stops, takes about a tenth of a second, okay? Then it's gonna fully stop, then it's gonna take another tenth of a second for that to expand. So this range is gonna go from 2.75 to 2.85 to 2.95. So she's gonna have a line that's gonna go something like this, okay? It's gonna be very steep, because what's happening, and again, keep in mind what the slope of a velocity time graph gives you. It gives you acceleration, which is the rate at which your velocity changes. So you can just watch that and go, wow, that was a big change in velocity. That stopped, slowed down, sped back up, and all that happened very rapidly. So that means that's going to be a steep line on my velocity time graph. So she's going to come back here to 2.75. If I want my pen. Okay? And that's when that's going to hit. Now, on the front side of the slab, down here, I've got a whole bunch of things that you need to have on that velocity time graph. Make sure that you have done all that. First thing, when the plunger hits, when the spring is compressing, when the spring is expanding, and when it leaves the wall. So I should clearly see all four of those points. So let me give you a hint. This point up here, when this line begins to dive down, that's when it's going to hit. Because something has to happen to change your acceleration. There has to be a different force acting on it. So when it hits, oh, that's going to create a different force. That's going to create a different acceleration. So then if you look at the sequence, right, you're hitting, the spring is being compressed, that's when it's slowing it down, right? So during that region when it's slowing down, that's when the spring is compressing. Mother Nature doesn't like that. Mother Nature sends it back in the opposite direction. That's when the spring is expanding. And then down here is when you're going to leave. Okay? So you hit, compress it, expand it, leaves. Okay? Think through the return trip. It's going fastest as soon as that plunger leaves the wall. Because as soon as that plunger leaves the wall, it begins to slow down. Okay? So it's going as fast as it's ever going to go as soon as it leaves the wall. So, you want to label velocity and acceleration. Don't come in here and put, oh, positive V and a positive and a negative sign. Okay? I have no idea what a positive and negative sign mean. I got nothing. Okay? I have no idea what that means. Now, if you think you have positive velocity, oh, put a positive V. If you think you have negative acceleration, which you should, then put a negative A. So in each segment, and there should be four. 1, 2, 3, 4. You should have 4 distinct segments. I want to know the sign of the velocity. I want to know the sign of the acceleration in each of those 4 distinct segments. Okay? You also want to label when it's speeding up or slowing down. Well, obviously from here to here, I'm slowing down because I'm approaching 0 meters per second. So I would put a down arrow here to indicate that I'm slowing down. Here I'm speeding up. I'm going to put an up arrow here. Okay? The up and down arrows don't indicate direction. They're going to tell me if it's speeding up or if it's slowing down. And if you want to figure that out, you can either look at the signs, look at your velocity and acceleration, see if they have the same sign or opposite signs, or if it's approaching 0 meters per second, you're slowing down. If it's going away from 0 meters per second, you're speeding up. Okay? I don't care how you think through it. Just pick whichever one makes the most sense for you. Okay? So, in each region, the sign of the velocity, the sign of the acceleration, is it speeding up, is it slowing down? That's what I'm looking for. Now, when you get to some of these questions, okay, be very specific when you're answering these, all right? Just don't say, oh, when the cart is at the wall, okay? There's a whole bunch of things that are happening when that cart is at the wall. The plunger is being compressed, the plunger is expanding, the cart momentarily is completely stopped. So if you just say at the wall, that's too nebulous, okay? Specifically tell me what's happening, okay? That's what you want to look for. Now, when you get to number 8 and 10, when you're going to calculate that area, here's the easiest way to do this. I'm going to draw this a little bit bigger, okay? So let's say your velocity time graph looks something like this. The easiest thing to do is to basically come across and treat it like a rectangle, where you basically take like the average height. So if your line is sloping down, make that horizontal line go about halfway in between. So you're going to lose some of that area here, but you're going to pick it up over there. And then this is going to be your height, and then this is going to be however much time you have. Eli.
Is it okay if I broke it up into like 2 triangles?
That's
and a
fine.
rectangle?
That's fine. They're an overachiever, good for you. Okay. Now, then you can do the same thing down here. Come across here with some negative velocity and multiply that by some amount of time. Hopefully what you should see is that the sums are pretty close to 0. Okay? And if you do this at all right, they should be. Okay? If you have a sum of 12, you have done something horribly wrong. Okay? Horribly wrong. All right? Now, let's talk about this question about friction on number 13. Okay? So, one of the things that when we start to get into this acceleration unit on this next unit. So here's the cart, okay, and it's rolling. And it's going to have some amount of velocity, okay? So when you have a certain velocity vector at some point in time, one of 3 things can happen when you look at it again. Either the velocity vector is getting bigger because it's sped up, the velocity vector has gotten smaller because it's slowing down, or it's the exact same and nothing has changed, okay? Well, clearly, when you push something, what does it do? Every time when you push something, what does it do? Eventually. Comes to a stop, right? Okay? And that's a whole philosophical debate involving Aristotle. But, yeah, every time I do this, it's going to come to a stop. I could do this all day. I do not have to worry about doing this and all of a sudden it starts going faster, which would be cool, right? So here's the deal. So I've given this cart a push, it has a certain velocity. So when I draw the next vector, that's a little bit smaller, and then it's going to get smaller and smaller and smaller, and eventually it's going to come to a stop, okay? So here's the rule. If your velocity vectors are getting smaller, your acceleration vectors are pointing in the opposite direction because it's making those get smaller. So in this situation, I draw an acceleration with -8 because that's in the opposite direction. So as this thing is rolling, you have some positive velocity vectors that are getting smaller because the cart's rolling and it's slowing down. So if you see velocity vectors changing, the only way that can happen is if there is an acceleration, and if the only way there's an acceleration if there is a force. So the golden rule of friction, whether I do this like the wheels or I flip it over and I do it like that, okay, doesn't make any difference. This way, wheels, doesn't matter. Friction always acts in the opposite direction of motion. So if you have positive velocity, guess what? You're going to have no, it's always in the opposite direction.
Negative.
So if I have positive velocity, I'm always going to have negative friction. Okay? Now, if you look at F equals ma, okay, if you look at F equals ma, Eli, is mass ever going to be a negative number?
No.
No, it's not, because mass is a scalar quantity. It doesn't make any sense to say, what's the mass of the ball? Oh, -2 kilograms. Really? Let's think that through. Okay? So mass can never be a negative number. Now, Ms. Hernandez, let's talk mathematics. If I have a positive mass and I have a negative acceleration, what sign does my force have to be?
Can you say that again?
I have a positive mass, because mass can never be negative. Okay? So if I have a negative acceleration, what sign does my force have to be?
Negative.
There you go. Okay? So force and acceleration always have the same sign. There's no exceptions to this rule whatsoever. I cannot have a negative force creating a positive acceleration. Okay? Can't happen. That's like saying there's a cool freshman. No, there's not. Okay? Freshmen are nerdy. That's just the rule. Okay? So if you have a negative force, you're going to have a negative acceleration. If you have a positive force, you're going to have a positive acceleration. No exceptions to that rule. None, 0, 0 whatsoever. Okay? So keep that in mind when you answer that last question on the test, or on that quick lab. Anything else you want me to go over? Now let me give you a hint. When you read question number 5 on that back side, it says, during the time the plunger is in contact with the wall, is this a large acceleration or a small acceleration? And then I say, explain in terms of change in velocity and time required. Guess what you might want to mention? Change in velocity and time. I'm just throwing that out there. Okay? You just might want to mention, was it a big change in velocity, a small change in velocity? Now, the other thing that I want you to keep in mind, in the context of this class, when I say acceleration, you have to get out of your mindset that that only means speeding up. If I'm talking about something accelerating, I'm talking about the velocity vectors changing. Velocity vectors might be getting bigger, velocity vectors might be getting smaller. We might be changing the direction of those velocity vectors. Okay? So get out of your minds right now. If I say, did the card accelerate? That does not mean the only time it was speeding up. If those velocity vectors are changing, bigger, smaller, it's accelerating. Okay? So keep that in mind. All right. Make sure, and I cannot emphasize this enough, on this velocity time graph, make sure that you have each velocity and acceleration labeled, when it hit, when it's compressed, when it's expanding, when it leaves, arrows indicating if it's speeding up or slowing down. If you're not sure if you have those, give your paper to someone near you and go, hey, can you figure out what I got going on? If they go, well, I got nothing, I probably won't either. Okay? So if you're not sure, ask a study buddy. Okay? Any questions at all? Dime, are we good?
Yeah.
Okay. Going once? And twice? Sold. So get that handed in. Tap paper pudding?
Yogurt.
By the way, hello?
There you go. Okay. So here's how this week is going to play out. So we have the graphical addition of vectors. That's why you need protractors and rulers. If you happen to have not seen the email,
Shame on you.
What do you say?
Shame on you.
or don't have one, I do have some spares. Okay. That's why the God made email. So today we're going to do the graphical addition of vectors. Tomorrow we're going to do trig with vectors. That's Wednesday. Then, and don't flip out, it's just sine, cosine, cosine, tangent. Then Thursday we'll review, Friday is your next big test, so the velocity. Okay? So that's how this week is going to play
Does that
out.
mean 2 tests on Friday?
In case you want to plan for
Yes,
social
we've been
contact.
knowing that. 2 tests on Friday.
All right.
Test?
Yeah.
So what we're going to start off with is called the graphical addition of vectors using the tit-to-tail method, which sounds horrible, okay? It's like, oh my God, it sounds so difficult, all right? You all intuitively understand how to do this. I just have to convince you that you know how to do it, okay? Literally, you get this I just have to put the math behind it. So, there's a couple of rules. First off, when you're doing this, okay, you're always going to start with some x and y axis. Now, what's going to be different, up to this point, we've defined things in terms of like positive and negative, okay? When you're doing vectors with the tip-to-tail method, we're going to change it up, and we're going to use degrees. So rule number one is that the positive x-axis is defined as 0 degrees. Okay, so that way everybody's starting with the same thing, that's 0 degrees. And we're going to measure everything around counterclockwise, okay? That's how we're going to define any angle. So if I say, hey, Riley's walking at 30 degrees, okay? What I'm going to do is I'm going to start here at 0 degrees, and I'm going to take that protractor, and I'm going to measure up 30 degrees, okay? So 30 degrees, boom, there you go. If I'm at 90 degrees, that's going to be straight up. If I'm at 180 degrees, that's going to be over here. 270 is straight down. And if I'm over here in this fourth quadrant, that might be like 350 degrees, okay? The reason that we do that is so that way we avoid negative angles. Because if Nick says, hey, I'm at negative 10 degrees, well, I don't know what that means. Negative 10 from where? Is that negative 10 from 0? Is that negative 10 from straight up? I don't know, okay? So that's why we set up this system. So 0 degrees, positive x-axis. Every angle is measured counterclockwise around from that. So we will never, ever, ever have negative angles, okay? Got that? So what this process allows you to do is come up with what's going to happen when you have two vectors or 3 or 4 or 5 acting at the same time. And it allows you to find like the net effect of this. And you can use this with any vector quantity, whether that's displacement, velocity, acceleration, forces, momentum. You can use this with magnetic fields, with electric fields. Anything that can be represented with a vector, we can use this exact same process. So it's such a cool multi-verse tool because so many things in physics are described using vectors. Now, sometimes the math department here tries to get into vectors, and they use weird things like, they use like IJK. Yeah, you know exactly what we're talking about. Yeah. It's just weird. We're going to use like X, Y, Z, okay? I don't even know where that came from. Anytime math tries to do physics, they just screw.
So it's like IG and like IJ.
Yeah.
It's like so easy to get mixed up.
Negative I's plus I.
Vectors
Yeah,
are a
it's
rough
just,
time in my
no,
life.
it's just.
I like doing
Okay, so let me show you an example of how you will know how to do this, okay? So let's say that we're going to have a tug of war, all right? And Riley's going to pull this way with a force of 20 newtons at 0 degrees. Now, because a force is a vector quantity, what two things do you have to have?
Oh, magnitude and direction.
Okay? Magnitude and direction. Those are the two things that you have to have. So the 20 newtons is the magnitude, and 0 degrees tells you which direction that she's pulling. Okay? So this is force Riley. 20 newtons at 0 degrees. I know exactly which direction that she's pulling. Okay? Now, Jack is pulling this way. So here's force Jack. And he's going to pull 15 newtons at 180 degrees. Okay? So Riley's pulling this way with 20 newtons. Jack is pulling the opposite direction, 15 newtons at 180 degrees. Okay, so what's going to happen?
It's going to go to Riley.
Riley overpowers Jack by how many newtons?
5.
5. In which direction?
To the
0 degrees.
0 degrees.
Okay?
Yeah.
Riley wins 5 newtons, 0 degrees, right? Congratulations, you all just did the tip-to-tail method of vector addition. You're going, no, we didn't. Okay? Yeah, you did. So here's, now that's what I said. You understand this. I just have to prove to you that you understand it. So what you do first, and when you draw it like this is what's known as a free body diagram. And we'll especially use these with forces. So a free body diagram, if you go into engineering, you'll take a class called statics, and you'll do a semester's worth of free body diagrams. You will learn to hate them. Okay? Everybody, unless you're really hardcore into vectors, then you really like them and you're weird. But, so, and we're going to draw a lot of free body diagrams. We're going to draw free body diagrams of forces. But what the free body diagram shows you is all the forces acting from a common center and which direction that they're acting. So drawn like this is not the tip-to-tail method. This is a sketch going, hey, Riley's pulling this way and Jack's pulling this way, okay? That's all that's showing. So we'll spend, when we get into forces, we'll spend days talking about free body diagrams. This is just an opening sketch that says, hey, this is what's going to happen. Now, when you draw it tip to tail, okay, the sequence is important. So I'm going to pick Riley's, and I'm going to draw hers first. So I'm going to come out here and say, okay, here's force Riley, which is 20 newtons at 0 degrees. Okay? I drew hers first. Now, here's what's going to be important. From the end of Riley's vector, now I'm going to draw Jack's vector. Okay? So imagine that I could cut this out, cut it, and I'm going to glue it at the end of Riley's vector. This is why it's called the tip-to-tail method. So I'm going to take Jack's. I'm going to go from the end of Riley's, and now I'm going to draw Jack's. Okay? So now I'm going to draw Jack's, which is going this way. So here's force Jack, which is 15 newtons at 180 degrees. Okay? Now, what you're after next is the most important part of this process. What you're after is what we call the resultant. The resultant is the net effect of the forces, the displacement, the velocities, the accelerations, whatever it is. Okay? Now, this is an Australian thing. R, matey, you going with the roo. Okay? It's a roo, it's a cracker. So, this stands for resultant, goes from the origin out. Okay? All right? So, here's the deal. So, what happens, crikey, matey. So, I'm going to start here, right? I'm going to draw that resultant. Let's go lava. It's nothing. Okay? So, there's my resultant. And this is why you have to draw it from the origin out. Okay? So, that resultant is 5 newtons. Now, if I just say the resultant is 5 newtons, is that enough information?
No.
No. Why not?
You need the
Where
motion.
Yeah, if I just tell you 5 newtons, cool. 5 newtons. All right. So what? Okay. That's just the magnitude. But what do you have to put with it?
Direction.
Ah, direction. So which direction is this vector going to point?
0.
At 0 degrees. Now, when I do that, it was weird. I had to like tap it to get the electrons to flow. Okay, it's weird. So now, so this is why it's the Australian thing. Crikey, matey, we're going from the origin out, right? Because if you did it wrong, if you go from here back, then you're going to say, Riley's pulling this way, Jack's pulling this way at 15, but we're actually going to go in Jack's direction by 5, which doesn't make any sense at all. Okay? This is why when you draw the resultant, you go from the origin out to wherever you end up. Okay? Now, here's another way that you can visualize this. Some people like a walking analogy, okay? So imagine that Maggie starts here. Maggie is going to walk 20 steps in this direction, okay? Because this is a displacement vector. Could be a displacement vector, anything that's a vector quantity. So Maggie walks 20 steps this way. She turns around and she walks back 15 steps to here, okay? Now at this point, she needs a spoon for her yogurt. Let's just say hypothetically, okay? You need a spoon for your yogurt. And Jack goes, hey, I got a spoon. Okay, good. So what happens if Jack is going to get that spoon to Maggie so Maggie can eat her yogurt is that Jack is going to walk 5 steps in this direction to get to Maggie because that's where Maggie ended up. Okay? Got that one? Pretty simple. Now we'll make it a little bit more complicated. Not bad. So here's another X and Y coordinate system. So here's a soccer ball, okay? So Topher is going to kick the ball this way. Force Topher is going to be 15 newtons at 0 degrees, okay? So Topher is going to kick the ball this way, going this direction, okay? Got that? Good? Fantastic. Now, at the same time, Morella is going to kick the ball this way, which is going to be 20 newtons at 90 degrees. Okay, so visualize this. Topher is kicking the ball this way, Morella is kicking the ball that way at 20 newtons at 90 degrees. Okay, simultaneously this is happening. Okay, Topher, where's the ball going to go? Between what and what?
45 and 90.
Okay, why?
Because Morella's taking more.
Okay, so Morella's applying more force. I know this thing is going to go somewhere up like this, right? It's not going to come down like this, which would be really weird. So yeah, you're kicking the ball this way, you're kicking the ball that way, the ball is going to go down here. Weird, no, okay? Now, Topher, you said more than 45, why? More than 45, but less than 90, why?
And that's the middle of both of them, and Morella has more force.
Bingo. This vector is bigger, okay? Morella is kicking it with more force. So that means it's probably going to be closer to this one. Now, drawn like this is the free body diagram. This is not how you do the tip-to-tail method. All I'm doing is painting the picture about what's happening. Topher's kicking the ball this way, Morella's kicking the ball the other way. This is going to be the net effect of it, okay? Now, if you're going to draw this tip-to-tail, we'll draw Topher's first. Okay, so here's for force Topher, which is 15 newtons at 0 degrees. Now, here's the whole thing. From the end of this, now, the end of Topher's vector, that becomes like a whole new X and Y coordinate system. So from the end of this, now I'm going to draw Morella's, okay? So, and that happened to be at 90 degrees. So from the end of this, I'm going to go straight up for 20 newtons. Oop, come back here. So I'm going to come up like this, boom, 20 newtons. Now, at 90 degrees. So this is why when you draw the resultant, again, you go from the origin out to where you ended up. You don't draw it from here back, okay? Because if you draw it from here back, you're going to say, oh yeah, Topher kicked it this way, Morella kicked it that way, but the ball is going to go down like this, which doesn't make any sense. So that's why it's so vital that you draw it from the origin out there. So I'm going to come in here, I'm going to draw this, oh, go away, go away. So I'm going to have something like this. Now, what you're going to do is that you are actually going to take, this is why you need the ruler and protractor. Like you would draw this to scale. You would say, oh, okay, there's 15. Boom. There's 20. Okay? You draw that. Now, then to get this one, you're going to take your ruler and you're going to measure this length. Okay? Okay, that's, you're gonna measure that. So that might be, I'm just gonna make up a number, 26.5 newtons, whatever it is when you measure that. Now, when you give the angle, remember, any angle has to be from the positive x-axis, okay? So here's 0 degrees. So I'm going to put this protractor here, 0 degrees, and I'm going to measure this angle, which in this case is like 58 degrees. So I would say the resultant is 26.5 newtons at 58 degrees, okay? Now again, if you, some people like a walking visual. So what we're saying is that Zoe started here, and she took 15 steps. She turned, she walked 20 steps this way. This is where she is at, okay? Dime says, Zoe, you forgot your boomerang, mate. I gotta get you your boomerang. So he doesn't feel confident throwing it because if he misses, it's just gonna come back to him anyway. So he goes, I'm gonna go on a bit of walkabout, right? So this is gonna tell Dime how to get from where Zoe started to where Zoe is now. So Dime would walk 26.5 steps at 58 degrees, okay? So there's two ways that I can get to this point. They both end up at the same point. Zoe walks out, turns, goes up this way. Dime just goes, I'm just going to start here and walk straight out that way, okay? But here's what's important. In both situations, you end up at the same point. It's just how you get there, okay? Got that one? Good. Okay. Now, here's the most complicated one. So, go with the soccer ball analogy again, okay? Let's say that Cooper's going to kick the ball this way. So Forrest Cooper is 20 newtons at 40 degrees. Okay, so Cooper's kicking the ball this way. And then, I don't know, Taylor's going to kick the ball this way at 30 newtons at 120 degrees, okay? So, visualize this. Cooper's kicking the ball this way. Taylor's kicking the ball this way, simultaneously, right? Franklin, where's the ball going to go? What's the angle going to be?
Me?
Yes.
Oh.
What did I say?
You said Franklin.
I'm sorry. I still have to keep it.
He did Franklin the turtle. No, I said it was something like
Fish.
Yeah.
There we go. I got the F part.
That's about it.
Okay, I know. I'm old. I can blame that on a lot of things. Okay, hey, you're lucky I got the F right. I could have called you Dalton. Okay.
There we go.
Yeah, okay, Fisher.
Yeah.
Okay. You're at 20, you're at 30. Where's it gonna go?
It's gonna go somewhere probably between 90 and 180.
Okay? Between 90 and 180.
Yeah. Probably
Okay.
100.
Could it ever go more than 120?
No,
So maybe somewhere between 90 and 120.
I guess.
We could narrow it down a little
I
bit.
was putting a quadrant.
Yep.
Yeah.
You can pick it a quadrant, yeah, somewhere up there. Okay. Why do you say that?
Because it's applying more force and then the other one's applying force in the opposite direction, so it couldn't go more, it couldn't go steeper.
Okay, I like that. So, since I got Cooper going here, Taylor going here, you know that that ball has to go somewhere between 40 and 120. So when I do this, if I get an angle that's not between 40 and 120, I've done something wrong, okay? And again, this is what we call a free body diagram. This is just showing what's happening. This isn't tip to tail. This is just giving me a visual about what's going to take place. So, if you're actually gonna do this, here's what you're gonna do. You're gonna start with an X and Y coordinate system, and you're gonna come out here and you're gonna measure, in this case, 40 degrees. So you're gonna put your ruler like this, and you're gonna make this mark at 40 degrees, okay? Come in here, you're gonna make that mark, and then you're gonna draw that line to whatever length that has to be to correspond with 20 newtons, okay? Go away, okay? So this is gonna be, there's 40 degrees, Forrest Cooper, 20 newtons. Now, when I draw Taylor's, okay, this is the tough part, okay? When you draw hers, this becomes like a whole new X and Y system. So imagine that we're going to take Taylor's vector and we're going to cut that out and we're going to glue it on right here. So when I measure that 120 degrees, imagine this is a 0 degree plane right there. There's my positive x-axis. Don't measure it like this, okay? It isn't going to be around from Cooper's vector. The only thing that I need Cooper's vector for is to define where that x and y coordinate system starts, okay? That's the only thing I need that for. That's it. I just need to get to this point. So I'm going to take my protractor, put this here, and in this case, I'm going to measure around 120 degrees. So there's 90, boom, there's 120. I make that mark. Then I'm going to come in here from the end of that. Whoa, don't try and overlay that. That doesn't work. And then I'm going to draw that line like this. So that's going to be, whatever that is, 30 newtons at 120 degrees. If it was 180, I draw it around like this. If it was 200, I draw it down something like this. So all this is doing is giving me the end of that vector, okay? So imagine that you're starting over from scratch. You're just taking this vector, you're going to come around like this. Now, when you draw that result, okay, you're going to take this and you're going to draw that line just like this, okay? So I'm going to come in here. Here we can get fancy. Whoa, how cool is that? Okay, so this is my result. This is what I'm after. Okay, this is my net effect. Now, here's the trickiest part. When you measure that angle, it has to be from this initial positive x-axis counterclockwise around to this. These vectors have nothing to do with it. All these vectors are telling you is how to draw this one. So when you're measuring this angle, it's from this axis around like this. So I'd put that like this, and I'd have like 88 degrees. So this would be, I'm just going to make up a number, say 28 newtons at 88 degrees. Okay? So that's going to tell me the length. Here we go. So again, this is like Michael starting here, walking, changing direction, ending up out here. So what this is telling me is which direction Sam would have to walk and how far he'd have to walk to get to where Michael is. So Michael goes, boink, takes the left, does this. Sam just walks straight out that way. Got it. Yes, Riley.
Do we need to figure out like the newtons for it?
Yeah, and that's what you would measure.
Okay.
So what you're going to do today is all like based upon lengths, okay?
Oh, okay, I get it.
But it could be anything that's a vector quantity.
Okay.
So typically what you'll do, like when we actually get into forces, you're going to draw, typically you might have to set up a scale, like maybe 1 centimeter equals 5 newtons. So if we're dealing with like really big forces, we might that 1 centimeter equal a newton, or 5 newtons. And so then you just draw it to scale, and then measure it and work backwards and figure that out. Yes, ma'am?
Does it matter which one you start with?
No.
It doesn't? Oh.
But typically what you want to do first, typically everything goes from like a positive x-axis. So it really does, because if you drew this one first, you would have just started here, and then you would have gone up like that.
Okay.
So the sequence, just like 2 plus 4 is 4 plus 2. You get there, but it's just in the opposite way. Okay? Now, let me hand out the assignment, and then I'll explain that. So, shut that down. Okay, so all of these are going to be based upon dimensions. Some people like to use notebook paper, some people like to use grid paper, so whatever works for you. The advantage of grid paper is that you always have a visual of your X and Y axis. So here's the first thing that you're going to do. This is going to be the easiest 5 points you will ever get in this class. So this is going to be based upon 5 vectors, A, B, C, D, and E. So up at the top, the first thing I want you to do is I just want you to draw these vectors. So that way you have a visual about where they are. So you can do this one of 2 ways. You can either like draw them out A, B, C, D, whatever. You can draw them separately, or you can draw them all from a common center. Okay? I don't care. And again, you are going to take a ruler. Like for example, on vector A, that's 5 centimeters. You are going to take a ruler and you are going to measure out a length of 5 centimeters. Okay? Boom, there you go. That's how long that's going to be. It is going to be exactly 5 centimeters. Now let me give you a word of advice. When you're drawing these vectors, draw that line like 5 centimeters. When you put an arrowhead on it, don't put your arrowhead on the end of the line, because then that's going to make it longer than actually 5 centimeters. Okay? So don't let your arrowhead make that longer. So again, you can draw them all from the same common center. You can draw them each separately. I care not. Make sure they're labeled so I know exactly what they are. Now, when you get to question number 2, we're going to add vector A to vector A. I'm going to show you exactly how I want this done. So on number 2, I want to draw vector A, which would be 5 centimeters at 0 degrees. Okay, boom. I'm just going to draw vector A. Boom, here we go. That's it. Now, I'm going to add vector A to itself. So I'm going to add vector A to vector A. So from the end of vector A, I'm going to draw another vector A. Okay? 5 centimeters at 0 degrees. Now, you don't have to write out this. Okay, some people like to, because the more information that you have, the better off. At least, at a minimum, label it what the vector is, A, B, C, D, E, so that when I'm looking at it, I know what you're drawing. Okay? If you want to write out the other information, that's cool, but at a minimum, at least label the vectors. Now, so imagine this. Okay? You walk 5 centimeters, or 5 meters, 5 steps, whatever you think about it. You're going to take another 5. So to get to where you're going to end up, you're going to start back with a drop pin. And you're going to start here, and here's going to be this resultant. Because remember, that resultant goes from the origin out. So Eli is going to walk 10 centimeters at 0 degrees. So this is going to be 10 centimeters at 0 degrees. So what I want to be able to see on another sheet of paper is something like this. You can take number 2. Here's number 2. Draw the 2 vectors, A plus A. Then you're going to draw the resultant vector. So what you want to write here on this sheet, where it says A plus A, what I want to see there is 10 centimeters at 0 degrees. That's the net effect. Now, here's what, some of you are looking for a pattern, and you go, oh, we'll just add together the length of the vectors. In this situation you do, because they're all in the same line. That is not going to be true if they're not in the same line, okay? So like on number 3, let me give you a sketch of what number 3 is going to look like. So in number 3, you're going to have A plus B. So you're going to draw vector A. From the end of vector A, you're going to draw vector B. And then you're going to draw that resultant. Okay? So let me give you a hint. This is not 8. Okay? You're going to measure this, and it's not going to be 8. So it isn't like 5 plus 3 gives me 8. So you're going to take your protractor, you're going to measure this angle, you're going to measure that length, and that's what you're going to write down. Now, the sketchiest one is number 4. So let me give you a sketch of what number 4 is going to look like. So on number 4, and again, this is just a sketch. So B is 3 centimeters at 90 degrees. So here's vector B. D is tough because D is 6 centimeters at 250. So to get D, that's all the way around from here, all the way down to 250. So what you have to do is realize this is 180 degrees to here. So if you take 250 minus 180, you get 70. So you're going to come in here and put your protractor like this, and then you're going to measure, there's 180, plus another 70 gets you to 250. So then you're going to draw that vector down like this, okay? So there's going to be vector D. So when you draw that resultant, so when you measure that resultant, that has to be around like this. So this is what number 4, this 4 is one of the tough ones to draw. So you're going to draw vector B. From the end of vector B, you're going to draw vector D. So that resultant is going to start here. You're going to measure around like this, and then you're going to draw that length. So that angle should be somewhere between like 180 and 270. So on number 4, that angle has to be between 180 and 270. Okay? So that's one of the more difficult ones. Okay, I'm done. You're on your own. If you need, there's some rulers up here. There's some protractors over yonder. Okay? They're not yours to keep. They're yours to borrow.